missed my fun story about my irrational 4-year-old and her love of curls. Sorry. Why can't you hear me? Because it was me. That's how it works. But nothing really important. So, today's a little bit different. And the reason it's a little bit different is because we're going to be talking about that, starting to be talking about that decision-making component of regression. So the idea of you have a lot of non-linear, non-procedural decisions that you make when you build models. There's not one way to do it. And so we're going to go through kind of lots of different examples, some of which you've seen, some of which you haven't, around why would you take out a predictor? Why would you add a predictor? What's a control variable? Why would you control for something? But this lecture is not do this, do this, do this, do this. It's not teaching you a new thing. It's just helping you work out a muscle you already have. That's the best way to think about it. You're not doing a new exercise. You're just working a muscle you've already started to build. So there's no demo. We're really just going to be talking and thinking. So questions are really good today. Questions about, well, would we build a model that looks like this? That will be really helpful for today. And I'm also going to pace today a little bit based on how we go. So if we're moving pretty quickly, then I may do everything that's in this deck. If we are not moving very quickly, I may skip the last concept, which is called suppression effects. The reason I might skip that, it's not on the exam, things I don't ever say, but there is a regression check-in, the simple and correlation check-in that I want to make sure we get to today, because that's going to be a lot of the foundation for our exam review on Tuesday. So that trumps, better word, never for lack of a better word, that overrides, takes precedent over the suppression effect. But we'll get to suppression effects are really cool. So it's just a cool regression thing to see. But I do want to start with the second categorical example because we didn't get to it. We went a little bit quick on Thursday. Your DA isn't due yet for categorical. And so it gives you another opportunity to get practice with the categorical piece. So we're going to do the second example that was in the slide deck. So this is a real estate example looking at predicting sale price for homes that are being built in 4 different cities. So these are the 4 main cities that I've lived in my life: Claremont, Ithaca, San Francisco, and St. Paul. Research shows that home price is best predicted by the linear combination of square feet of the property and city. Lord, would I love to buy a house in St. Paul or Ithaca over Claremont or San Francisco now. Take a minute. I want everyone to take a second now, and I want you to write down the full model equation. And you can go ahead and assume that the continuous predictor in here, which is square feet, was centered prior to entering it in the analysis. But everyone needs to have that equation kind of off to the side as we go through the questions we're going to go through. So full equation. I don't care if you use Y's and X's or if you use the actual variable names. What if people, I am curious though, what have people been using when you jot stuff down? Do you usually use Y and X or do you usually use the actual names? Actual names, so mixed.
Depends how long the name.
Depends how long the name, fair, fair, yeah. Lisa, bless your heart. I recognize that background. We have it. So it should look this. Because we have 4 levels of our categorical predictor, we need 3 dummy codes, and it can start to get a little bit hairy to remember them. So what's our reference group? Claremont, because it's got zeros across the board. Ithaca is D1, so I might even just say Ithaca here. And then D2 was what?
San Fran.
And D3 is St. Paul. Great. All right, now you're gonna group up. 2s or 3s are fine. If you're wedded to 4s, that's 2. And you're gonna tackle these 9 questions. I'll give you 15 minutes, 10 to 15 minutes. They looked a lot of questions, but some of them should be it's there, 1 second answers. But I'll circulate and sort of get a gut check for how long people need. So go ahead, and then online I'm gonna do breakout rooms, so you have small groups to work with. All right, go for it. No islands. Yes. Say that again? Yes.
Oh.
Can you unmute and say one thing so you're at the top of my?
Hi. Hello, 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 hello.
Yeah.
Private bingo 76. That's what they are. Really? Oh, because you don't they also it just
We were wrong. They were gonna call.
Yeah, well, it happens.
Can we rejoin the breakout room?
Can we return?
Oh yeah,
that?
we can. Yeah, we can.
Where can we find that room?
It says join breakout room, and then it says room 4
Where does it say that?
on the bottom panel. Be
Oh
right.
yeah, that's true. Do we go backwards to stay here?
I look, you don't see where it says that, but
Yeah.
like you're adjusting that.
I was just fixing the screen wasn't mirrored. So I was fixing the mirroring on our screen. Or I should say it was mirrored, because I couldn't see it. Yeah. All right, let's go. Last. Okay. So we're gonna go over each one quickly. What is the predicted home for a house in Claremont? So let's just start with that. Claremont is the reference group. So automatically 0, 0, 0. No biggie, we can get rid of these away with average square footing. Okay, remember that our data are centered. So what is this? What is the predicted home price when all predictors are average? The intercept. That's our answer. No math needed. Now, that's not enough to memorize that that's the predicted home price. The question is, why? Because the intercept is always the predicted y value when all x values are 0. We are still plugging in a 0 here. Let me show you why. Here is your graph. This is square feet. This is housing price. Let's hypothetically say that the average square footage lies here on the x-axis. I'm just making that up. I don't have the raw data. And that the average housing price when square foot is average is up here, 687,726. And we know it's positive slope. Let's say it's, I don't know, yay. So that's what it looks uncentered. When we center our continuous predictor, what we do is we take every dot and every point on the axis and we subtract the mean. So if this coordinate here is the mean of x and then this 687 value, and we subtract the mean, what is the x value going to become? 0. All that's going to happen is this is going to move over here, and this is going to move over here to the x equals 0 position. So it's still the predicted value when x equals 0, technically, but because we moved all the points over, the location of x equals 0 is actually that average point. That's why this is the predicted value of the home for Claremont when square footage is average. Okay. So if you actually say the intercept is always the predicted value of y when x equals 0, centered or not, we can just say that when it's centered, the value at x equals 0 is actually representative of the average because we've just shifted it over to the x equals 0 position. Yes.
And hypothetically, you can do it with any other kind of stack. You can do it with a median.
but we don't median center, we mean center. I mean, you could subtract 7 from it too, hypothetically, but we don't, we subtract the mean. Yeah, just the mean.
Jessica,
Yeah,
so say it wasn't centered, because I thought when it's centered, the predictors are at the average mean, but when it's uncentered, then the predictors are at 0. But in
Yep.
all cases, then just assume that
it's, let's think about it this way. It's the predicted value of the y when x is at the 0 location, at the origin. Does
yeah,
that make sense?
yeah.
So the location is always x equals 0. It's whether the value of the x value in the data is actually truly 0, or if it's actually x at the average of x and we've just moved it over to a different location. What's the predicted home price for a house in Ithaca with average square footing? How do you figure it out?
You input a 1 for where it's respectively for the dummy code and 0s for all the other ones because we're using center data.
So we don't use this one. This one goes away. Wait, no, which one's Ithaca? First D1. This is why we don't name things D1. Ithaca, SF. Good. So these go away. So we have $687,726 plus 366.0 because it's at the 0 axis. So this is the predicted price. This is the predicted price for a home with average square feet in Claremont. We want the predicted price for a home with average square feet with only one difference. Now, instead of being in Claremont, we want it in Ithaca. So all we have to do is subtract $429,702. And what do we get?
$3,024.
Cool. All right, what's the predicted home price for a house in San Francisco with average square footage? Same concept, 687,726, but now we have to add the 1 that represents San Francisco. And then same concept with St. Paul. Start with our intercept, which is the average home price in Claremont, and change it to St. Paul. Question?
Yes,
Yeah,
the intercept in this case sounds it's the average home price in Claremont. Is that what you're saying?
yep.
I don't understand that.
It's the average, it's the predicted home price for it's not the average home price in Claremont. It's the predicted home price for a house in Claremont with average square footing. That's very different.
Yeah, I'm just having trouble connecting the intercept with the whole thing. That just happens to be also the average home price in Claremont with average square footing.
Close your eyes. Everyone close your eyes. Raise your hand if you're still confused. Listen, keep your hand down. All right, put your hands down. What? No, Jason, open your eyes. Jason just asked if he can open his eyes again. Everybody else had their eyes open already. So if we have, what does the intercept represent in robotic terms? The predicted score on Y when all X's are 0. So this is the predicted score on Y, predicted home price when all X's are 0. We good with that? Yeah? Questions about that? So now, let's go ahead and put a 0 in for all of our X's. Good? Well, first of all, what happens to all of our terms mathematically? They just go away. And all we're left with is 687. That's why it's the predicted Y when all X's are 0. But let's start with this chunk. Does putting all zeros in mean something?
Yes,
Yeah, what does it mean?
it means we're in Claremont.
It means we're in Claremont. It means it is this dummies coding scheme. So we've got that part down. So now we at least know that it's a predicted home price in Claremont. We're good with that. Now the question is, what about this guy? Well, isn't that the predicted home price for a house with 0 square feet?
No.
And the answer The quick answer is no, because the data are centered. But now let me show you again why that would be. Here's the uncentered version of the data. Here's the centered version. There's the average square feet of a house across the whole data set, not in Claremont, across the entire data set. This is how much the model predicts a house should cost when square footage is average. Are we good? If that's our model, and I say, hey, this is my line, there's my model line. How much should a house cost when X is average? Well, I go, I find average X, I go up, the line says it should cost this much. Guess what that much is? It's 687 if I'm controlling for this. Oops, sorry. Here, if it's centered, then we've moved everything over so that this X equals 0 point actually represents or is conceptually the mean. You see that? And now that same point is at the y-axis. But is that the average price for everybody, or is that the average price only when these are also 0? Only when these are also 0. That's really important. So this is not the predicted home price for every city with average square footing. It's only the predicted home price, as Daisy said, when all the X's are 0. So when square footage is average, as in this is a 0 at the origin, but also these are also 0. If we plug in anything other than 0 into these 3 dummy codes, this number is going to change. Does that help? You'll see it in the graph too. I have them graphed on the next slide. Here's what they look, by the way. All right, what's the slope between square footage and home price in Claremont? 366. What's the slope between square footage and home price in San Francisco?
366.
Good. Why does this not change? Well, how many coefficients do we have in here attached to square foot? 1. Here's 366 and here's square feet. There is nothing in here that can touch 366x. There's no 2x we're gonna add on to it, no minus 3x we're gonna add on to it. 366 is the only number that ever gets multiplied by x. 366 is the rule that is across all cities. So it's the slope no matter what city we're in. That's an important concept to understand. It's the main effect of square feet, because once we get to moderation, that won't be the case. We're gonna change it up. Then how do we write out the simplified model equations? We just took what we did in part 1 and we put it together with what we just did. The intercepts are gonna change depending on whether we put 0, 0, 0, 1, 0, 0, 0, 1, 0, or 0, 0, 1. That's gonna change the intercept, the predicted home price for a house with average square feet in that city. But the relationship, how many dollars the house is gonna increase for a 1 unit increase in price, that won't change. That's going up by 366. And here's what it looks like. Graph. Questions? That was worth the time. Question. Good. Glad we did another example.
Yes.
Okay.
So we had just a number to plug in. So if we had not an average, not the concept of an average, but a number to plug in, would we use uncentered data in that case?
So in this particular equation, if this was the only equation you had, Allie, you can't use uncentered data. Why? Because the equation is centered. So it's the idea of apples, apples, oranges, oranges. So if your equation is already centered and you don't have access to the equation with an uncentered intercept, you have to use centered data. So for example, if you were like, screw Claremont, I'm moving to Ithaca and I want to buy a house. And you were like, I want to buy a house and I want to know how much it's going to cost. And it's in Ithaca and it's, I don't know, big. It's 3,000 square feet. How would I predict? But I'm still stuck in Claremont, so I can't actually, and I have no internet for some reason. So I can't just check Zillow. So I have to use a regression equation to predict the housing price, because I'm that nerdy. So how would I do that in this equation? Yeah, so the first thing I have to do is to enter my X. I have to take 3,000, which is my raw X that I'm putting in, and I have to subtract the average square foot. You'd have to have that. And then this part's easy. I can be like, it's in Ithaca. It's not in SF. It's not in St. Paul.
So you have to kind of manually center your variable that you're putting
You
in.
have to, yes, you literally have to make, yeah, you don't even have to you do have to center your variable. Yeah, now you can say to R, you'll see it in the demo, you don't have to search for the mean. You can say, X minus, and then you can write mean of X. So it will find the mean for you. But yeah, if I were, that's why it's important, it might be a really good exercise for you to think of what are the versions of equations that we've looked at. Standardized, unstandardized, centered, uncentered, and which are best for what. Because if you ask me, hey Jess, I'm running a model and I want to know what predicts what's the first thing I'm gonna look at? Betas and p-values. I don't give a you know what about these. I don't care. I'm not even looking at the intercept. If I want to predict an outcome from raw values, which equation am I always going to want to use? Uncenteredized, unstandardized. Because I just want to plug in the data I have. So it's not one is better or worse than the other. They literally are they're the same model. I keep using the language analogy. It's the same sentence in different languages. But a phrase in Russian would not be very helpful in Italy. It's the same concept. If you're trying to plug in raw values, a standardized equation is not helpful. So it's like, what are you trying to do with it? And therefore, what value is helpful in that case? Cool?
Just a follow-up question on that.
Yeah, Lisa.
Do you always subtract do you always subtract the average from your value versus your value from the average when you're...
Yes.
So it'll actually be negative if the average is greater than...
Correct. Yeah, because what you want to represent is your price greater or smaller than the average home price, average square footage. So if the average square footage is 5,000, then you are looking at a house that's smaller than the average square footage. So it's a negative representation.
Thank you.
Good.
Is the intercept, when we have a categorical variable, still considered a fixed parameter estimate?
Oh, interesting. Yes, it's still fixed. That's actually a good follow-up to Ray and JJ and Brett and Lily's question, because they were, oh, this is fixed. Even if it were moderation, by the way, guys, it's still fixed. When we talk about fixed or random, oftentimes we're talking about allowing the individual data to have different rules. In this case, it's still, that's a really hard question. Would you call it, I would still call it a fixed parameter, but it's.
You haven't seen the wrong thing.
Would you call it a random intercept?
Saying that
It's random at the,
intercept
random.
But the slope is fixed.
The slope is definitely fixed. Yeah, it's random. It's random, but you have to be careful because it's not random at the individual data level. It's random at the group, at the categorical variable level. Yeah, just be careful about what level you're talking about. Yeah.
It's not.
Yeah, but if it's one intercept for everybody, that's just purely fixed. You can also do random intercepts where you allow everybody in the data set to start at a different point. Especially if you're doing longitudinal analysis, that would be. What if I were interested in whether the relationship between city and home price was significant? Just city and home price. What are my options?
A single city or just?
No.
Run an ANOVA.
Run an ANOVA is one option. What if I wanted to use just regression?
Can you compare two models?
I can't compare two models because I can compare two models, but that is doing something a little bit more specific. If I just want to know the relationship between city and home price,
You could just run a simple regression.
there you go. Can I look at the correlation table?
Yes.
No, why not? They're dummy coded. City is dummy coded and it's splitting it up. You've got D1, D2, D3. I'm not looking at city and home price. I'm looking at the difference between Ithaca and Claremont and home price. Not to mention, it's not continuous, so that R doesn't make sense. It's two clusters of dots. So if I don't want to consider square footage, I can run a regression. It's technically not a simple regression. I get why you called it that. I would call it that too, actually. Conceptually, it feels simple because it's one construct, but it's actually three variables. So it's technically a multiple regression, but conceptually a simple regression because it's one construct predicting one construct. Yeah, run a regression with all of your dummy codes and look at the R squared. That's it. That's the variance in home price explained by city. What if I wanted, or I could run an ANOVA and look at the ADA, which is going to be the same as the R squared as we saw on Tuesday. Or if I wanted to consider square footage, then I go with Jason's idea. I start with a model with just square feet. Then I add on my city, and then I see whether the delta R squared is a significant change or not. But when you do it the second way, you're asking whether city explains significant more variance above and beyond square footage. You're not asking, does city explain variance in home price? You're asking whether city explains significantly more variance in home price above and beyond square footage. Couple announcements, and then we'll just keep talking about models. That's what we're gonna do today. We're just gonna talk about models. Exam 1 is next week. I'm spending my Valentine's Day grading. Yep, it's gonna be great. With my favorite. I'm very excited. I love grading. That's true.
That's true. Valentine's Day.
And I have a Valentine's Day present video that I always show that I can't wait to show you guys next week. I'm gonna have to show them early, huh?
You want.
Because I can't show them on exam day. I always play a video for my stats class.
Great for review day.
It is good for review day. I always play a video for Valentine's love song for my stats class on Valentine's, and usually it's on Valentine's, but.
It's been a year. I feel I watched that video in this class a couple weeks ago.
That's because you've seen it 7,000 times. I'll play it for you on Tuesday. Add your questions to the review link by Sunday. I'll finish the review Monday morning. One quick thing, we're gonna have a check-in at the end that you'll start in class and finish afterwards, just so you don't have to sit here the whole time if you don't want to. You do not need to ask to do one of the things that were in the check-in. Does that make sense? We're gonna go through the check-in as part of review. So put your conceptual, your other questions, your hypotheticals, but you don't need to be, can you go over number 5 from the check-in? Because we're gonna go over all of the check-in. And then number 11, the 11th, next Tuesday, review, exam practice, and then Thursday exam. The rest of this is going to be called Spurious Waffles. You'll see why in a little bit. Now you're hungry, yeah. All right, this is a good meme for today. Me trying to control every possible variable in regressions. What are the objectives? Really, today is just thinking about how do we build sound statistical and theoretical golems or models. And the goal is not, this isn't a mastery lesson. You don't walk out a day being, I got it. I can build perfect models. And like I said, it's really just about working out that decision-making muscle. And then the way you get good at this is you just keep doing research and you keep running regressions and you come across funky stuff. And then you're like, oh crap, how do I deal with this? And you talk about it with somebody and then that builds that muscle more. So I could teach a whole semester where we just look at weird models and decide what to do. It'd be a fun class. Problems in linear regression. So remember that the goal of statistics, specifically in regression, is to explain as much variance, but that's representative of being able to essentially describe or predict or explain the truth, what's happening out there in the population, as best as we can. With the understanding that we have no way, like 1, we'll never be able to do it, and 2, we have no way of actually really knowing if we got it or didn't get it. We have indicators, we have things in our toolbox that give us more or less confidence. We think we're more or less accurate, but we really don't ever know. Bummer. I'm just inspiring you all to go do research. So there's really 2 big approaches to modeling. I'm gonna look at this one first. in regression. The first is when we test what we call a priori hypotheses. So that is when we build a model a priori before we run analyses, and we actually theorize a relationship using theory, using past empirical evidence, and then we test that theory using regression. Okay, that's if you read journal articles for class all the time, that's what you come across 95% of the time. The other is more of an exploratory approach. That's, I wonder what contributes to job satisfaction. That's not very common. How many times have you read a research article that's like, I was just curious what predicts happiness, so I threw a bunch of variables in and checked what stuck. No, there's a lot of reasons for that. That's where p-hacking comes in, throwing a bunch of stuff and sees what's sticking. We do this sometimes in regression class purely for the purpose of learning how to interpret models. But normally we're going to have an actual hypothesis and we're going to test that hypothesis. You don't get to change your hypotheses when you test them in your research. I say this to my directed research class. There is a chance that every single one of your hypotheses will not be supported. That's okay. Now, can you run other models after that? Can you re-specify? Sure, but you have to be transparent that you're now in exploratory mode. Hey, my model didn't fit, so I re-specified in this way and found XYZ, or I explored in this way and found XYZ. But not super common to actually run models this way. Much more common to run models this way. What we've been doing is this process of hierarchical linear regression, which is the idea of building successive linear models by adding or removing predictors and comparing model fit. Usually it's forward in direction. So we start with one predictor or no predictors, use one. We start with one because the F tells us what no would be. And then it's conducted by you. It's not conducted by R. You decide what to add. And here is a very important key takeaway. If you have controls in your model, we will always run a model with just your controls first. So if you have a study and this person wants to test this model and they're controlling for this, their first model should just be their controls. Okay, why would we do that? Yeah.
If you want to make sure.
Can you talk louder so they can hear you?
Because imagine if you added a control and suddenly the model explained the variance in the dependent variable, then you're not, then it's just over because like the control actually I think influences it.
Yeah, you want to make sure your actual predictor of interest explains variance in your outcome above and beyond your control. And you want to know by how much. Good. Quick grammar or vocabulary distinction. Hierarchical linear regression is not the same as hierarchical modeling. Really annoying. Sometimes you'll see the term hierarchical modeling as representative of what I call multi-level modeling. We're going to touch on multi-level modeling in D. It's a specific application of regression when your data are nested and have two levels. But hierarchical linear regression is not the same as hierarchical modeling, where you have nested data. So we're just going to look at some models, some of which we've seen, some of which we haven't. And like I said, we're just going to practice the what do we see, what would we do next kind of decision-making process. There isn't really always an answer. And as I do this, I'm going to try to plug a couple holes that I'm seeing in interpretations and DAs. So this example you've seen, we looked at it on last week. This is the job satisfaction example. And this is an exploratory question. So what features of the workplace best predict job satisfaction? We've got supervisor support, conditions, colleagues, workplace, tasks. Now, if I'm going to go with this type of model building, again, not super common, this is more of the exploratory. I'm not using theory necessarily. This is a data-driven approach. So if I'm taking a purely data-driven approach, my best resource usually to start is my correlation table. If I want to build hierarchically, meaning I want to add in coefficients or add in predictors, I tend to start from a data-driven perspective with whatever predictor has the strongest relationship with my outcome. So in this case, job satisfaction, so we look down, and my strongest predictor is conditions, followed second by supervisor, okay? So here's my model, and I'm gonna build one at a time so that I can see the impact of each subsequent predictor. Now, here's my model output, and more importantly, here's my model fit. So, does model 2 explain more variance than model 1?
Yes.
Yep. How about 2 and 3?
Yes.
How about 3 and 4? How about 4 and 5?
Yeah.
Interesting question for you. Does this always happen this way, do you think?
No.
That once it's significant for a little bit and then everything else after it is not significant? Could that last one be significant? Yeah, this last one could be significant again. It just means that adding in workplace made the model better. That's a signal to you that we gotta run some different models. We gotta change the order of how we run things. Here is what we call, when we put everything in it, we call it a saturated model. Okay, that means if all predictors are included, saturated model. Some people just start hierarchical regression and go backwards. So they start with a saturated model to see how things work together, and then they take away. So they actually play around backwards. There's a difference between models you play with in R and the models you then sort of write up in your manuscript. You can play with models that you don't formally write up in your manuscript. Yeah.
Is there any benefit to doing it like backwards rather than the way we've been doing it?
I'm going to say, my personal opinion is I don't take a purely linear way either way. I actually don't think it matters where you start, because wherever you start, you should end up in the same place. Sometimes I will start backwards and then I will get all the way down, and then sometimes I'll go back and go the other way. That's what I mean by you can play and run 15 models and then actually decide which hierarchical progression is the progression to put in the paper. Does that make sense?
Yeah.
Yeah. So here is that saturated model. And we talked about this before. When saturated models can be really helpful for figuring out what's happening in your data. So this was that example where we looked and we saw, wait a second, supervisor and colleague weren't significant anymore. And when we looked at the collinearity stats and we looked at the correlation, we're, oh, they're really highly correlated. That's one of the things that can lead coefficients to become not significant. When something becomes not significant, when you add in something else, what that means is that something else is doing enough of the work to predict the outcome that this doesn't really matter anymore. I want to look at this one. Here's your DA. So your DA asks you to test researcher 1 and researcher 2. That's it. Researcher 1 said professionalism and competence. Researcher 2 said professionalism, competence, and motivation. So here's professionalism and competence. Here's professionalism, competence, and motivation. You had a delta R squared of about 20% difference. Definitely significantly more variance explained in success. And that was where your DA asked you to stop. Is that where you would or should stop as a researcher based on what you see in this model? Good. This is the decision-making model. This is why I didn't have you do that, because all we're at is interpretation. But now we're starting to build that decision-making muscle. Looking at the output, what do you see? Couple things.
Motivations is the only. It's
not. Yeah.
Professionalism and competence mattered less when motivation was considered.
So professionalism and competence matter way less. This was the model you ended up, isn't this the model you ended up? Oh, sorry. Professionalism and competence matter way less when motivation is considered. Yes, but even more specific than that. Where do my eyes go first? Beta P. So remember, for interpreting, your eyes should go to every single number in this table. For storytelling, beta P. So for storytelling, if we look at the beta and the P, it's not just that, it's even more specific than that. Yes, professionalism and competence matter less, but how much less? Yeah.
I got curious when I was for the BA, so I read it again.
Yay, good.
And it turned out that when you do it individually, all of them have the similar. thing. So like usually it's kind of not just the same amount of people.
So she said she ran all of the simple regressions, basically. So if you run simple regressions on all three, they all look like they matter. Do you need to do that though? Where else can you see that? The correlation table. If we look at the correlation table, they did all relate or correlate with success. That's what led the researchers to be like, these are all important. That's why they argued about their hypotheses. But we still haven't gotten the story down from this table. Yes, motivation matters more, but there's more than that. Yeah.
I ran the third model.
No, I want the story. Yeah.
So they're no longer significant with motivations.
Which one?
Or
No, we know how to read p-values. Yeah.
Competence is at 0.05, so it's not.
Is it below 0.05?
Yes.
Yeah. Is the cup, this is below 0.05. This is a positive confidence interval.
We go to 3.
Just because you round something doesn't change that a number is below 0.05. 0.04999999999999 is still less than 0.05. Now, is it a huge coefficient? No. This is the idea of thinking versus rote. Yes, it is still significant, but it has way less of a contribution. What becomes completely irrelevant? Professionalism. We gotta practice the storytelling, guys. It's when you consider somebody's motivation, their how professional they were in undergrad is no longer predictive of how successful they are post-college, and their competence stays predictive, but very, very, very slightly predictive, small relationship. And motivation has this massive prediction. Now, why? Let's post hoc theorize, as I call it. We don't know why, but why might that be? Yeah.
If you're motivated, you're more to work on yourself to be more confident, be more professional.
Good. Think about somebody who's motivated. Well, if I'm motivated, then I can work to be more competent and I can work to be more professional. Anybody ever go to school with someone who's extremely competent, but really lazy? Yeah. I had a partner like that for a long time. Not very successful. Competence on its own is not predictive if not paired with motivation. And professionalism, same thing. You can be professional, but without the motivation, that's not enough to take you. So if you take motivation out of the equation, yeah. If that's the only information I have, it looks like it predicts success. But remember, just because, this is an important thing to remember too, just because something's not in our model doesn't mean it's not out there in the world functioning. Motivation is still out there. Just because we're not measuring it doesn't mean it's not at work. So once we captured motivation, we saw competence and professionalism both drop. That's actually where I would start. And then I would go one step further and say, so much so that professionalism actually didn't matter anymore. And competence still mattered, but to a very, very, very small degree. Yeah.
In that part of the analysis, might you also talk about the tolerance and the VIF?
Yes, absolutely. Yep. If I don't have it here, but absolutely you could say of note, there was a strong correlation between professionalism and motivation and competence as indicated by tolerance levels, and then give them. Yep. Yeah.
And our data in this DA, there was violation of homelessness. So I don't think that this model can be predicts really, but this model doesn't maybe fit everyone because we didn't have data on success with low success. So it was only high success. The average for success is really high, 73 something.
Yeah. Good thing to notice.
And I think that when we speak about highly successful people, the motivation really matters.
Yeah,
And confidence and professionalism draw. But if we would see data on less successful people, so probably all three could matter.
good, great. So where does that all go?
Discussion.
Yeah, that's brilliant research discussion. And what you would do is you would pull in theory to support that. Absolutely. Motivation might be a distinguisher when you're talking about people who are highly successful, but that doesn't necessarily mean that that's the same differentiator when people are less successful. So she was talking about the data being heteroscedastic and us not having a lot of data for people at lower levels of success. And as I said, it's not you stop. It's most important that what would be dangerous is if you didn't notice that, make sense of it and talk about it. It's as long as you notice it, make sense of it and talk about it and discuss its implications. That's how real data works. The data you get in the DAs, save this one, is prettier and nicer than most data you will ever get. Your data will almost always have some issue that impacts your interpretability, your conclusions, etc. That's part of that muscle building. That's why I always say the answer are in the data. The answers are in the data. You have to get to know what your data looks like. Descriptives, visualizations, because that are where all the answers to the implications of your model. And answers to are all of the, why did I violate X, Y, Z? Why did this happen? Why did this thing that happened that I didn't expect to happen? I'm always gonna tell you, people have sat with me and been like, Jess, this weird thing happened. And the first thing I always say is, pull up your data, graph your data for me. I need to see, I have no idea until I look at it. I could not possibly fathom why that happened. Sometimes I can get clues in the regression table. Here I got a clue. I was like, huh. The tolerance levels are kind of related. And also these are constructs that I'm really familiar with. I can post hoc theorize why these might be related, but that's not always the case. Sometimes I'm working with constructs that I'm not familiar with when I'm helping somebody. And that's where I really have to pull all the things I have. I have coefficients, I have tolerance, I have graphs, I have raw data, I have descriptives. It's all of those things together are breadcrumbs. That's the way I think about it. They're breadcrumbs as I try to figure out what is happening here in order to figure out what is happening out there. I ran another one. So after seeing how high motivation was and seeing how not that high confidence was and how not at all significant professionalism was, what would happen if I ran a model with just motivation? And then I added onto that confidence. Because the other thing we always have to remember is whatever outcome we're predicting, how much variance is there to explain? Kind of a weird question, but it's not a trick question. Yeah, we could only explain 100%. So even when a predictor is not significant, look at this 0.03, negative 0.03. It's still eating, I use that word, it's not significant, but it's still eating a little bit of the variance in success. That's part of the reason why we opt to take out things that are noise, because they still eat variance in our outcome from our data. So I opted to run, one other thing that I went over yesterday with someone. This negative 0.03. If I asked you, is there a relationship between professionalism and post-college success, what would you say? Yeah. In this model?
Yes.
Is there a relationship between professionalism and post-college success in this model?
Yeah.
I see a lot of yeses.
Oh.
Why are we saying yes before I freak out? Why, it's not 0, yeah?
It's not a significant one and it's very weak.
Yeah.
Because you're asking if the relationship is in this model, this data set, not in the population.
Good. Well, I want to draw something for you to help you understand how that beta and that p-value actually can be interpreted together. Because the reality is this model is telling you that there is no relationship. There is no relationship. The beta is not a relationship. The beta is the line of best fit. It's the coefficient. But what is the coefficient always weighed against?
Nothing.
No, it's, yes, nothing. That's the null hypothesis.
Yeah.
But it's coefficient relative to what? Error. You're forgetting the error part. There is no relationship between, yes, AJ, you're up. There's no relationship between professionalism and success in this model. And here's why that would look. Let's say that you have a predictor. I'm going to do a different predictor. You have X predicting Y, and then you have A and B also predicting Y. In your model, the beta for X is 0.10 and the P is 0.234. And I'm, is it significant? And you're, yes, in this model, there's a relationship, but it's not significant. No, there's not. Here is why. The slope is 0.10. I can draw that, yay. But do the dots fall on that line? No. The dots are yeah. So what is this part? That's the standard error. That's error. So the question is, what is driving this? This is the t-stat. What's the ratio in the t-stat? Slope or effect? Yeah, effect. Ooh, remember I said that would never change? I didn't lie to you. Slope or effect over error. So we see slope, that's the line. That's 0.10. That's the thing that's making all you all go, oh, there is. But you're forgetting the error part. What you can do in R, and I'll show you at some point after the exam, is you can actually show the line, but shade the error around it. And watch what happens when I shade the error around it. Hold on. What's the null hypothesis in the t-test? Oh my gosh, I've asked this 5 times. You got it. Come on, you can do it. What am I testing this against?
0.
0. The null hypothesis is B or beta / the slope is 0. I am testing whether the slope I obtained, whether that 0.10 is actually different than 0. Well, guess what? Visually, once you shade that error, what I'm really asking myself is, can a flat line fit in that shaded error zone? And the answer is yes. That's why it's not significant. That line, really, the true relationship between X and Y is somewhere in the yellow. Remember, we're inferring out to the population. That red line is the line of best fit in this data set. But the relationship is somewhere in the line plus error zone. Hence the confidence intervals, guys. Don't forget those. That's what that shaded area are. So if that zone, if that confidence interval includes flat, i.e. if the confidence interval includes 0, then your line is no different than nothing. So now, when we look at a regression table and that P is not significant, and I say, is this a significant predictor of this? The answer is no. We can say the line of best fit, the estimated slope in this model is this, but that slope is not significantly different than 0. Cool? Cool.
Jess, can you ever have a variable that's added that makes something significantly reverse its directionality?
So, yes, you can, absolutely. You can even have not significant predictors emerge as totally significant when you add something. That's called the suppressor effect. It's at the end of this slide deck. We're not going to get there today, but we will get there. You don't need it. You don't need it by Thursday. It's just a cool thing to learn. I want to do one more thing, and then we're going to start. That's enough for today, just playing. We have time after the exam to play more. We have a whole open 2 hours. This is the one that I wanted to play with real quick. This is closing a gap from BAs that I saw. So here we have a new study. Here we're explaining performance. Model 1 explains performance from drive. Model 2 explains performance from drive and communication. Model 3 explains performance from drive, communication, and networking. I'll give you a second. Think, don't blurt it out. Which is the strongest model or the strongest set of predictors that drives performance?
Model 3 explains the most variance, but it's not statistically significantly more than Model 2.
Which means in the language of stats, it's kind of the beta that we just saw. It doesn't actually explain any more variance. It's just happens to be a slightly larger number in this 277 person sample. So rather than saying it explains more, but it's not significant, I want us to get that but it's not significant out of our verbiage. It's because we don't care about the sample. That's not why we're doing this. We're doing it to decide what's out there. Our sample is representative of that. So if the change is not significant, you're noticing that actually Model 2 and Model 3 are explaining the what? Exact same amount of variance. It's kind of when we did t-tests, you remember that? And it would be like the mean of group A is this, and the mean of group B is this. So if we said the mean of group A was 4, and the mean of group B was 4.5, are they different? And you'd be like, well, they're a half a point different. It's like, no, they're not statistically different, they're not different. That's it, yeah.
So when they explain the same amount, then do you refer to parsimony?
Yes.
And say that it's Model 2 would be
Yep.
the best fit?
100%. And now we're going to get into that clarification that I wanted to clarify on the next slide. So now the question is, so what have we decided? Model 2? Yeah? Okay, cool. So which model explains the most variance in performance? How are you going to answer this? Model 2. There's one answer. Okay? Now, hey, Hannah, what explains the most variance in performance? And she answers me Model 2. I'm gonna be like, yeah, I don't know what Model 2 is. So this is the other shift I want us to make, is we don't do stats to do stats. We do stats to answer questions about the world. No one cares about your stats, they care about your answers to the world. Well, I care about your stats. And stats nerds care about your stats. But really, people care about the answers that your stats allows us, the questions your stats allow us to answer. So really, it's that the combination of, this was, oh, we have to change this. I changed the example because I didn't want you to use the same. What was it? Drive and communication?
Yeah.
Just change it so we don't screw it up. Really what I found was that it's the combination of an individual's drive and their communication that best predicts or explains performance. That's what I found is the best predictor. I didn't find Model 2. I don't know what Model 2 means. Now, Model 2, the Model 1, Model 2, Model 3, that's really helpful for organizing your manuscripts. So I will always use that, but I'll sometimes put that in parentheses. Or I'll say Model 1, which explains performance from blank and blank. But I always try to make sure that my results section is focused on what I'm studying, not the results rote that I'm running.
Hey, Jessica,
Now, yeah.
do you ever, when you're writing something up, do you say in the context of this study, because it could be there's a predictor out there that you didn't think about that nobody's measured that actually is a better predictor, but you're basically talking about in this study, this was the best model.
Yes, although remember that your results section is coming after your entire front end of your manuscript usually. So you've already given your hypotheses that with this set of variables, this is what we're working with. So you've probably already set that caveat a little bit.
Yeah.
And then you're right that in the discussion, you're probably going to be, this study didn't measure everything. Here's other things we might want to consider. But yeah, good, at least a good reminder in your brain of this is not the best in the world. This is the best in this study. So then how do we know? It's not enough to be this. Now is where the stats come in. This is the best, but how do we know? How do you defend it?
Change in R-squared.
Okay.
Less variable.
So how is somebody in here, how would you defend this? We know we're gonna use delta R squared. I'm gonna give you 3 ways you might defend this. One that's insufficient, one that's sufficient, and one that's better. Here's insufficient. Model 2 explains significantly more variance than Model 1. Delta R squared, 0.12, P, I don't even know if I have it. I don't have a charger box, so that's not gonna help me. Oh, you do. Why is this insufficient? There's two reasons. If you wrote this as evidence for why a model was better, this would not be sufficient. Why? Two reasons.
One, it's not in context.
One, it's not in context. I don't know what model 2 is, I don't know what model 1 is, and you haven't mentioned your outcome at all. There's another even more important reason. Great. I'm curious. So you told me model 2 is better than model 1, but what about model 3? Was model 3 better than model 2? If you don't include that, then you're not complete in your rationalization. That's really important. So here's one that I would say is sufficient. Model 2 explains significantly more variance in performance, at least include the outcome, than model 1, delta R squared, but model 3 does not explain significantly more variance in performance than model 2. This is fine, especially when you're writing a stat section and you've already told us what all the models are. If you've already told us what the models are, then this is totally fine. And it's concise, which is beautiful. If you haven't told us what the models are, then here's one that's completely all-encapturing. A model predicting performance based on an individual's drive and communication, model 2, explains significantly more variance than a model predicting performance from just drive, model 1. Additionally, the addition, I probably wouldn't use addition twice, of networking, model 3, did not predict significantly more variance in performance than drive and communication alone. Delta. Yep.
So is the principal personally just assume you don't have to say by principal personal?
It's not a principle of, there's
Okay,
not.
sorry, it's the argument for
No.
personal. I guess we just have to explicitly say it.
But your rationale is, no, you don't need to.
Okay.
Yeah, you don't. There might be a time where you opt to choose something for parsimony that you would need to say it, but in this case, no. Because you're basically saying, I have two things that are exactly the same. One that has two things, one that has three things. Why would I predict with three things? So why did I play that? We've already talked about spurious correlations. Deja, however, stopped chatting. So he mentioned that piece at the end, which is super important, which is science before statistics. The only thing that makes our models causal is the theory that we imbue them with. So I love this idea of the causes of data can't be extracted from the data. No causes in, no causes out. So the reasons for why we do our data, our analysis are not in the data, they're in the causes of the data and the theory, the theoretical models that we build before we analyze. So why do we build models with more than one predictor? Well, it reduces the variance in our error. Okay, if we predict something out there in the world with one thing, that one thing doesn't predict a lot of variance. There's a lot of other things that predict variance. So we get more precise predictions and lower confidence intervals, narrower confidence intervals, because our parameter estimates become more precise. Now we're considering the effect of X on Y, accounting for these other things that are also happening out there in the world, whether we measure them or not. And it removes some bias in our theoretically modeled causal estimates, even though it's not actually, can't prove causality, but we're theoretically modeling causality in our models. I'm going to skip this. So one of the other things that we often do, other than just using focal predictors, is we use control variables as a way of also narrowing the precision of our focal predictors. And control variables or controls are things that we think might impact our outcome, but that are not of interest to us. So we want essentially to, and if we think about it from a causal perspective, it's what things might cause our outcome other than our predictor. It's the idea of let's rule out alternative explanations. Yeah.
Do you sometimes use things or variables that are already been studied or predictors that have already been studied?
Totally. Yeah. So the way I kind of think about choosing controls, and I have a couple slides, is there's one common group of controls. That's demographics. We often want to know whether a relationship holds regardless of a certain demographic. But the other type of variable are other possible explanations. That can come from past literature. Literature shows, for example, that relationships are the #1 driver of well-being in the PERMA model. you know, the PERMA model. Well, when Stuart was adding on financial well-being, he would have had to control for relationships to show that financial well-being actually contributes above and beyond relationships. So you're not always controlling just for demographics, you're controlling for other potential explanations to show that your explanation still predicts unique, that's the beta, still contributes unique variance in your outcome, even when accounting for this other thing. So statistics is not the only way to control for stuff. You can control for stuff in your design too. So you can use sampling control. So if you want to control for gender, for example, you can only recruit a single gender or separate by gender and see if the relationship holds amongst different identities. Or you can do experimental control, randomization. That helps with control. You're basically randomizing out the error. But if you're using survey design and field methodology, then that's really hard. So we're often doing statistical control. That's including variables as predictors in the regression model. So here are some examples. Some of these are demographic, but some of them aren't. So if you're interested in whether a medication reduces illness, then you want to control for other possible explanations of why illness might go up or down. Oftentimes when I have a model, I'll take my outcome variable and I'll go to somebody who's familiar with it and I'll say, what else might explain this? Now, can you capture everything? No. But having a couple control variables can often allow us to see how our unique predictors contribute above and beyond. Now, does R know the difference between your controls and your predictors?
No.
No. When you draw them, so when you draw your theoretical model, so let's say this is, let's do that performance one. So if this is performance, so this is drive, this is communication, and let's say that's my theoretical model. If this is my theoretical model that I'm hypothesizing, this is all I draw. My controls don't go into my theoretical model. It's not part of my theory. Thank you, Siri. Right? It's not, whoa, it's not part of my theory. But it would go into my regression table. It doesn't even need to go into your final figure if you don't want to. There's two places to put it in your final figure if you want to include it. One option is, some people put them over here to just indicate, hey, I'm controlling for these. And some people put them in the note because you don't want your controls to distract from the thing you're testing. So some people will say this model controlled for GPA and then in parentheses, beta P, blah, 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 beta P. So you can put it in the note of the model, but it keeps the figure focused on the things you're predicting. I think that's where we're gonna stop for today. Yeah, that's where we're gonna stop for today. There's lots more around model building that we can cover, but final reminder around controls, they go in first in their own model. Yeah.
When you're doing controls, to keep it clear, do you kind of annotate that it is a control so you know in your model building that it's a control and not another variable?
In your data?
Yeah.
I mean, here's my assumption is if you are at the point where you're running your data, you've already spent approximately, I don't know, 300 hours with the front end of your paper. You know what your predictors are, you're not gonna lose track.
I guess my real question is when it shows up in the regression table, do you need it annotated?
Nope. Oh, no, good. Yeah, in the actual regression table in your output?
Yeah.
No. But that is part of the reason why I do not put them in the figure. I don't put mine in my figures. Because I want my figures to reflect what I hypothesized. Because I'm not interested in my control. I'm interested in this relationship controlling for my control. So I will put it in the note and I'll say this model controlled for the following, and I'll put the betas in there, or I'll say C table 2 for all coefficients. But in the table, I always put everything. There's lots more about playing with models and things that can happen and suppression effects to Allie's question, which we can play with post-exam. Here is what I need you all to do. There is a check-in. You'll hate me now and thank me later. Kira did it last year.
I didn't hate you.
No, I know,
Okay,
but it's long.
it is long.
Yes, it's long, but a lot of them are true, false, yes, no, one answer questions. I opted whether I was gonna do this in class, out of class. Ultimately, I decided I was gonna start it at 11 and let you decide if you wanna stay and just finish. That would be my recommendation. If you have to go, you can go. So I'm giving you the choice, but I do need you to finish it ASAP. Ideally, I'm gonna say ideally today, but it would be if it were the end of tomorrow, but that makes me worried that some of you are gonna be, that's fine, I'll do it tomorrow. I can start the review as soon as they're all done. Let me put it that way. I can't start the review till they're all done because the review will have results for each question class-wide. So I really can't start it all until every single person is done with the check-in. Do not use your notes. Do not use your notes. Again, it is if you get a 0, then you'll know what you need to review before next week. I think that's it.
You go over DA3 stuff.
What about it?
That's.
Oh, DA3 is due Tuesday. Oh, thank you. This is really important. DA3 is due Tuesday. A reminder per the syllabus that if you do not turn in your DA on time and you do not communicate, it's gonna get a 0. This is particularly true. Well, it's always true, but this is really true. This DA, no extensions. Gotta turn it in on time because you're turning it in on review day, which means the TAs don't have time to give you feedback before the exam. So we want to be able to release the key. But we can't release the key until we have everybody turn it in. So turn it in on time so that we can release the key so everybody can get the feedback and nobody gets a 0.